What does it signify when a celestial wanderer appears to take breaths? 3I Atlas, a visitor from a distant star system, is expelling 40 kilograms of water every second into the frigid expanse, a location far too remote from the sun for such an active display. Observers are whispering, it's exhibiting signs of life. However, this celestial body's narrative extends far beyond that. Peculiar nickel devoid of iron, cyanide trailing behind it, and hints of origins that predate our own solar system by billions of years. Meanwhile, far removed from this interstellar traveler, citizen scientists have discovered the most substantial odd radio circles yet observed. Mercury and a planetary series are aligning with uncanny synchronicity in the October firmament, prompting speculation about a potential connection to 3I Atlas, and Blue Origin's October launch has generated more queries than it has resolved. Did it even transpire? Remain with me until the conclusion as we delve into these disquieting questions in our inaugural novel multi-part presentation, designed to keep our late-night audience abreast of all cosmic developments occurring above our heads. If these enigmas have captivated you as profoundly as they have me, be sure to press the like button and subscribe so you do not miss a single update. As this story unfolds in real time, leave a comment indicating your location, the current time there, and your conviction regarding whether we are receiving the complete truth about these world-altering discoveries. And if you wish to aid this community in its expansion, share this video on X, Facebook, Reddit, or even within your group chats. You are the reason we can continue to pursue narratives like this. Therefore, thank you for your unwavering support. Part 1. The Impossible Signal. Envision this scenario. You are adrift in the profound silence of space, situated more than 3 times the distance from the sun as Earth. In this remote domain, sunlight is a mere murmur. Ice remains eternally frozen. Comets enter a dormant state. All existence seems to slumber. And then, you witness it. A comet, unequivocally hemorrhaging water into the void, spewing 40 kilograms of this substance into space every single second. Not a meager trickle, but a veritable deluge. Water gushing forth from a frozen mass where its presence is entirely unexpected. This is 3I Atlas, an interstellar comet that has entered our solar system from an unknown origin, carrying with it the customs of another star's domain. And these customs, they do not align with our own. The initial indication emerged from SWIFT, a space telescope engineered for the detection of gamma-ray bursts. SWIFT directed its ultraviolet sensors towards 3I Atlas in early 2025 and detected something extraordinary: a luminous envelope of hydroxyl molecules encircling the comet. Hydroxyl, or OH, is what results when solar radiation cleaves water molecules. It is the residual echo of water as it disintegrates. The presence of OH signifies that water was recently present, and SWIFT observed an abundance of it. The figures are astounding. At a distance of 3.51 astronomical units from the Sun, 3I Atlas was releasing 1.35 multiplied by 10 to the 27th power water molecules per second. This equates to 40 kilograms per second, every second. For perspective, this is akin to discharging the equivalent of a small automobile's mass in water into space every minute, at a distance where our comets barely manifest any activity. Comets within our solar system do not exhibit such behavior, not in this region. So far from the sun, they remain frigid, dormant, virtually inert. Water ice requires thermal energy to sublimate, to transition directly from a solid to a gaseous state without passing through a liquid phase. And the solar energy available at this distance is insufficient to drive such activity. Our comets await their arrival much closer to the sun before they awaken and begin to emit gases and dust into space. 3I Atlas, however, seemingly bypassed this memo. You might recall Oumuamua, the initial confirmed interstellar visitor. That object was as dry as a bone. No water, no outgassing, merely a tumbling rock traversing our vicinity. Silently. Following that, we encountered C-2019 Q4, Borisov, the second interstellar comet. Borisov was indeed active, but its behavior mirrored that of our indigenous comets. It adhered to the established protocol. It was predictable. It was, in the most favorable sense, unremarkable. 3I Atlas embodies neither of these characteristics. It is animate in a manner that defies conventional understanding. It is vociferously expelling water into space where profound silence ought to prevail. And the central question occupying the minds of every astronomer who has focused a telescope on this entity is straightforward. How? What phenomenon could possibly be responsible for this? Could some exotic form of ice unknown to us be involved? Something that sublimes at temperatures we once considered too frigid? Is the comet's interior still retaining residual heat from its formation billions of years ago? Is it rotating in an unusual manner that concentrates solar energy onto concealed reserves of volatile substances? Or is there an internal chemical process occurring within that rocky mass that we have simply never encountered before? The water is merely the initial revelation. 3I Atlas is also emitting other substances, cyanide, nickel, carbon dioxide in proportions that defy logic. Each new observation introduces another layer to this enigma. Each spectral signature detected in the data represents an additional unanswered question. This is not merely a comet behaving erratically. This is a comet that appears to be operating under an entirely distinct set of physical principles. Principles established in a different stellar environment under varied conditions with differing chemical compositions. And now it is present within our solar system, affording us an unparalleled vantage point to observe processes previously unknown to us. The factor that keeps astronomers awake at night is this. If 3I Atlas is accomplishing feats that our comets cannot, what does this imply about its origin? What kind of stellar system gives rise to comets of this nature? What were the environmental conditions within that protoplanetary disk billions of years ago? And, most compellingly, is this comet simply anomalous, or is it a harbinger bearing tidings of the universe's potential for profound diversity? Every telescope capable of observing this object is presently directed towards it. Spectroscopy, photometry, polarimetry, every investigative tool at our disposal is engaged, because 3I Atlas is not merely an object of curiosity. It represents a portal, a fissure in our comprehension, and through that fissure, we may glimpse something extraordinary. Part 2. Nickel without iron. Comets are expected to conform to certain observable patterns. As their temperatures rise, metals begin to sublimate from their surfaces. Iron and nickel are typically observed together, much like inseparable companions on a journey. The presence of one invariably indicates the presence of the other. This is one of those cosmic certainties upon which we have come to depend. However, 3I Atlas appears to have disregarded this established principle. The Very Large Telescope in Chile directed its spectrograph towards 3I Atlas and detected a phenomenon that defied explanation. Nickel emission lines were intensely prominent within the spectrum, strong, unmistakable, and impossible to overlook, and iron, either entirely absent or present in such minute quantities as to be virtually undetectable. Nickel unaccompanied by iron. It is akin to observing smoke without any source of combustion. It is comparable to finding footprints without any discernible source. Within our solar system, such a scenario is unheard of. When a comet heats sufficiently to release metallic elements, iron and nickel appear in consistent ratios because they are intrinsically bound within the same mineral structures. They originate through analogous processes. They sublimate at comparable temperatures. They are chemically bonded in a manner that ensures their co-occurrence. But 3I Atlas evidently formed in a location that operates under a different set of rules. At an approximate distance of 2.8 astronomical units from the Sun, astronomers measured nickel emanating from the comet at a rate of approximately 5 grams per second. 5 grams may not seem significant until one considers its continuous release, second after second, with no discernible iron present. This is not an anomaly. This is a discernible pattern. This is the comet imparting fundamental information about its composition. Several hypotheses have been proposed, and none are straightforward. The first potential explanation involves chemical fractionation. It is conceivable that in the environment where 3I Atlas originated, nickel became incorporated into volatile compounds that readily vaporize, while iron became entrenched within refractory minerals that require substantially higher temperatures to sublimate. Imagine nickel hitching a ride with volatile ices, while iron remained sequestered in rocky grains, thereby creating the decoupling we are currently observing. Another concept centers on organometallic compounds. On Earth, we encounter molecules such as nickel carbonyl, where nickel atoms form bonds with carbon monoxide. These compounds are volatile. They evaporate at relatively low temperatures. If 3I Atlas formed in an environment rich in carbon monoxide and other organic materials, it is possible that nickel became entrapped within these molecular structures. When sunlight interacts with them, they decompose, releasing atomic nickel into the coma, while iron remains bound within solid grains. Then there is the possibility of space weathering. Cosmic rays and ultraviolet radiation bombard interstellar objects for millions or billions of years. Such prolonged exposure can induce peculiar alterations in surface chemistry. It is possible that radiation processing has generated nickel-rich surface layers, while iron has either become buried or undergone chemical transformation. Perhaps the nickel we are observing is merely a superficial layer, a rind altered by radiation that does not accurately reflect the comet's intrinsic bulk composition. Or, perhaps, and this is the most intriguing possibility, 3I Atlas originated in a stellar system with genuinely distinct elemental abundances. Stars do not possess uniform chemical compositions. Older stars, stars from disparate regions of the galaxy, stars that formed from gas clouds enriched by different types of supernovae. Each possesses a unique elemental recipe. It is plausible that 3I Atlas originates from a location where nickel was more prevalent relative to iron than it is in our immediate cosmic vicinity. Perhaps its progenitor star was chemically anomalous, and that anomaly is now imprinted upon every molecule of this comet. However, caution is warranted here. Spectroscopic analysis is inherently challenging. Detecting faint emission lines against a bright backdrop presents considerable difficulty. There are inherent limitations in detectability. It is possible that iron is present just below the threshold of detection. The iron emission might be obscured by other spectral features. We might be observing at incorrect wavelengths. As the comet approaches the Sun and experiences increased heating, iron might eventually become apparent. This outcome, in a sense, would be reassuring. It would signify that the universe still adheres to predictable principles. But what if it does not? What if 3I Atlas reaches its perihelion, the point of closest approach to the Sun, and iron remains undetected? What if the nickel-to-iron ratio continues to be completely inverted compared to all our prior observations? Such a revelation would be transformative. It would indicate that planetary systems can produce comets with metallic chemistries so divergent from our own that our current models would require substantial revision. This is precisely why astronomers are observing 3I Atlas with such intense scrutiny. Each observation serves as a critical test. Each spectrum offers an opportunity to either validate our existing understanding or fundamentally challenge it. And at this juncture, 3I Atlas is contributing more to the latter than the former. Part 3. A comet that switches on. Comets are anticipated to gradually increase in brightness as they approach the sun. The underlying physics is straightforward. Increased solar radiation leads to increased heating, which in turn results in enhanced sublimation, producing more gas and dust. This relationship should be linear, predictable, and rather unremarkable. 3I Atlas, however, seemingly disregarded this protocol as well. Observers monitoring 3I Atlas noted an unusual characteristic in its coloration. Initially, the comet presented a relatively neutral hue, perhaps slightly reddish, which is typical of distant icy bodies. But as it drew closer to the sun, it began to acquire a distinct green coloration. This was not a subtle shift, but a vivid, almost ethereal green that became unmistakably apparent in photographic imagery. This green luminescence originates from two sources: cyanide molecules and atomic nickel. Both emit strongly in the green portion of the spectrum, and both began to intensify dramatically as the comet warmed. The increase in brightness was not linear. It was not a smooth progression. It was superlinear, meaning the emission lines were augmenting at a rate exceeding what basic geometrical considerations would predict. When considering the distance to the sun, one receives 4 times the solar irradiance per square meter, governed by the inverse square law, a fundamental principle of physics. However, the emissions from 3I Atlas were escalating at an even faster pace. Something was being unlocked. A novel process was being initiated. Astronomers refer to this phenomenon as switch-on behavior. Imagine a specific temperature threshold. Below this threshold, a particular type of ice remains solid, contained, and dormant. Then, as the comet crosses this threshold, that ice suddenly begins to sublimate. The gas production rate escalates. New emission lines appear within the spectrum. It is akin to activating a switch. At one moment, the process is inactive, and at the next, it is fully engaged. And once initiated, it can potentially escalate exponentially if sufficient material is available to sustain it. 3I Atlas appears to possess multiple such switches. The water sublimation commenced first, at 3.5 astronomical units, which is already anomalous. Subsequently, the cyanide and nickel emissions began, manifesting a brilliant green hue as the comet continued to warm. Each emission suggests the activation of a different volatile reservoir, with distinct chemical environments reaching their activation thresholds. One proposed model that might account for this involves extended icy grains within the coma. Instead of all the activity originating at the nucleus's surface, envision small ice grains being ejected from the nucleus by the escaping gas. These grains drift away from the comet, remaining cold and frozen. However, as they travel, they are increasingly exposed to solar radiation. Eventually, each grain reaches its individual threshold and initiates sublimation. This creates a distributed source of gas, not solely originating from the nucleus, but also from a surrounding cloud of icy particles. This could explain the superlinear increase in brightness and the sudden appearance of new emission lines. Another possibility is thermal fracturing. Comets are essentially agglomerations of ice and rock. When one section heats and expands while another remains cold and contracted, internal stresses develop. Ultimately, a a fracture occurs. When ice fractures, it can expose fresh material that was previously shielded. Suddenly, new surface area becomes available for sublimation, and new volatiles are released. The comet experiences an outburst. 3I Atlas might be fracturing itself as it heats, revealing successive layers of frozen chemistry. Then there are the exotic ices. Water ice sublimes at one temperature. Carbon monoxide ice sublimes at a considerably lower temperature. Carbon dioxide's sublimation point falls somewhere in between. If 3I Atlas is structured like an onion, with different types of ice at varying depths or in different regions, then as it warms, a sequence of activation events would be observed. First, the highly volatile compounds, followed by the normally volatile ones, and finally, the more recalcitrant materials, each layer peeling back like chapters in a book. This phenomenon is not entirely unprecedented. We have observed comets within our solar system exhibiting unusual behaviors. Some comets experience sudden outbursts, increasing in brightness by a factor of 10 or more overnight. Some comets disintegrate as they approach the sun, succumbing to thermal stresses that overwhelm their structural integrity. Some comets remain dormant until very close to their perihelion and then erupt into intense activity. However, 3I Atlas is exhibiting these phenomena on a timescale that deviates from our past experiences. It is active at distances where it should be quiescent. It is activating in ways that seem almost intentional, and the tension is mounting. As 3I Atlas continues its inward trajectory, will further switches be engaged? Will we observe the emergence of new emission lines? New molecules that we did not anticipate? Will the activity level plateau, or will it continue to accelerate? Each week brings new data, new surprises. This is not a comet exhibiting steady, predictable behavior. This is a drama unfolding in real time. Part 4. Where did it come from? Every celestial object carries a narrative encoded within its trajectory. Its future path reveals its past, and the trajectory of 3I Atlas tells a story spanning billions of years and thousands of light years. Its orbit is hyperbolic. That is the technical term for an open curve, a path that does not loop back upon itself. 3I Atlas originated from interstellar space, swung around the sun, and will depart once more, never to return. Its eccentricity exceeds 1, signifying that this comet is unbound, an independent entity, a cosmic wanderer. It is merely passing through. Astronomers meticulously traced its path backward using pre-discovery images. Pre-discovery observation involves searching through archived survey data for images of an object captured before its significance was recognized. It transpired that 3I Atlas had been photographed on multiple occasions by automated surveys. Some images dated back to when the comet was 6.4 astronomical units away, still approaching, still cold and distant. By correlating these observations, astronomers progressively refined its trajectory with increasing accuracy. And that trajectory points outwards, back into the galaxy, but not to an arbitrary location. Orbital modeling, coupled with data from the Gaia Space Telescope, which has meticulously mapped the positions and motions of billions of stars, enables astronomers to formulate informed hypotheses regarding 3I Atlas's potential origin. The deduction is surprising. The galaxy possesses structure. The stars are not randomly distributed. The majority of stars, including our Sun, reside within the thin disk, a relatively planar region populated by younger, metal-rich stars orbiting the galactic center. However, there is also a thick disk comprising older stars that follow more inclined, more eccentric orbits. These thick disk stars are vertically dispersed, extending farther above and below the galactic plane, and they exhibit distinct chemical compositions. They are older, having formed earlier in the galaxy's history when fewer heavy elements were present. They possess lower metallicity. The trajectory of 3I Atlas suggests it may have originated from the thick disk. If this is the case, if this comet formed within that ancient stellar population, then it could be older than our solar system. Our solar system is 4.6 billion years old. Stars in the thick disk can be 7 billion years old or more. This implies that 3I Atlas might be carrying ice and rock from a period predating the Sun's very existence. Consider the chemical implications of this. The gaseous cloud that collapsed to form a thick disk star 7 billion years ago contained fewer heavy elements than the cloud that gave rise to our Sun. Supernova explosions enrich the galaxy over time, seeding it with elements heavier than helium. The earliest generations of stars consisted almost exclusively of hydrogen and helium. Subsequent generations, like our Sun, contain a few percent of heavy elements mixed in. Stars in the thick disk represent an intermediate stage. They possess some heavy elements, but in lesser quantities than we find in our solar system. If 3I Atlas formed in that environment, its composition would reflect that lower metallicity. There would be a deficiency of iron, magnesium, and silicon, all the rocky elements that constitute planets. But there would still be an abundance of volatiles, carbon, nitrogen, and oxygen, bound within ices and molecules. Perhaps this explains the exceptionally high carbon dioxide to water ratio we are observing. Perhaps it accounts for the anomalous metallic ratios. It is conceivable that this comet serves as a chemical fossil from an era when the galaxy was younger and the periodic table was less complete. Of course, certainty is elusive. Tracing an object's history through billions of years of galactic motion is a complex endeavor. Gravitational influences from passing stars, interactions with the galactic spiral arms, all these factors contribute to obfuscating the trail. However, the mere plausibility that 3I Atlas predates our solar system is extraordinary. We may be observing a relic, a survivor, a time capsule from the ancient galaxy. And if we could precisely pinpoint its stellar nursery, the group of stars that coalesced from the same gas cloud, we might someday identify its kin. Other comets, perhaps even planets, ejected from the same system, now dispersed throughout the galaxy. 3I Atlas could be a single letter within a message written across thousands of light years, and we are only beginning to decipher its meaning. Part 5. What's riding along with it? Comets are more than just ice and rock. They function as transport vessels, carrying the molecular constituents of their formative environments. And 3I Atlas is transporting some remarkably unusual cargo. We have already discussed the water, 40 kilograms per second, streaming into space at distances where such an outflow should be impossible. That water, or more accurately, the hydroxyl fragments that remain after solar radiation dissociates it, was the initial indicator of this comet's anomalous nature. However, water is merely the beginning of this unfolding narrative. Carbon dioxide presents the true astonishment. Observations suggest that 3I Atlas possesses an exceptionally high ratio of carbon dioxide to water. In comets within our solar system, water typically predominates. It is the primary volatile, the principal driver of activity. Carbon dioxide is present, certainly, but it plays a secondary role. 3I Atlas reverses this established order. Measurements indicate that 95% of the gas released is carbon dioxide, with water present in a smaller quantity. This is quite unexpected. It's the reverse of what we typically observe from comets in our own solar system. The question arises, why would a comet exhibit such a high concentration of carbon dioxide? One plausible explanation relates to the temperature at which it formed. Carbon dioxide ice solidifies at warmer temperatures compared to water ice. If 3I Atlas coalesced in a warmer region of its protoplanetary disk, closer to its originating star, it might have preferentially captured carbon dioxide while losing some of its water content. Alternatively, the radiation field of its parent star might have been different, altering the ices in ways our Sun does not. It's also conceivable that any giant planets within that system, if they existed, migrated in a way that disrupted the disk and mixed materials in unforeseen ways. Then there's the matter of cyanide. Cyanide, or CN, is a common component in comets, and it's responsible for the distinctive green hue seen in many of them. However, in 3I Atlas, the cyanide appeared after the water, later in its warming process. In contrast, cyanide and water in our comets tend to emerge around the same time due to their similar sublimation points. The delayed appearance of cyanide in 3 Atlas suggests it might be sequestered differently, perhaps locked within organic molecules that require significant energy to break apart, or frozen in layers beneath the water ice. And of course, there's the elemental nickel, glowing green independently of its usual companion, iron. While we've already delved into that particular enigma, it bears reiterating. Every element, every molecule we detect serves as a clue. Volatile compounds provide insights into the temperature and pressure conditions during formation. Refractory materials offer information about condensation sequences and thermal processing. The ratio of gas to dust reveals the comet's structure and its propensity to fragment. Now, let's address the most compelling possibility, the panspermia hypothesis. This theory posits that life, or at least the fundamental components of life, can propagate through space via comets and asteroids. 3I Atlas possesses water, organic compounds, and cyanide, a critical precursor in prebiotic chemistry. If one were to engineer a comet for the purpose of seeding a planet with intriguing chemistry, these would be the exact ingredients included. However, it is crucial to emphasize that this remains purely speculative. There is no evidence to suggest that 3 Atlas carries life, nor is there any evidence that any comet has ever harbored life. The panspermia hypothesis is captivating and theoretically plausible, yet it is unproven, and significant challenges exist. The harsh environment of space presents formidable obstacles. Over millions of years in interstellar space, high-energy particles relentlessly degrade complex molecules, a process mirrored by the destructive power of ultraviolet light from stars. DNA, proteins, and even simple amino acids are susceptible to destruction. For life to endure an interstellar voyage, it would necessitate deep burial within the comet, shielded by substantial layers of ice and rock. However, complex molecules, not necessarily living organisms, but rather chemical remnants, might survive. These molecules, synthesized within the comet's parent system, perhaps in a planetary atmosphere or on its surface, and subsequently incorporated into the comet, could withstand the journey if they are sufficiently stable and well protected. Analyzing them could unlock information unattainable through other means. They might illuminate the atmospheric chemistry of an alien world or reveal metabolic pathways from an extinct biosphere. They could, in essence, be messages encoded in carbon, nitrogen, and oxygen, awaiting decryption. This prospect fuels the ambition of some scientists to intercept these interstellar visitors. The goal is not merely to observe them from Earth, but to dispatch spacecraft capable of matching their velocities, landing upon them, drilling into their interiors, collecting samples, and conducting analyses. The technological hurdles are immense. Interstellar objects traverse at considerable speeds, tens of kilometers per second. Capturing one would demand a spacecraft already strategically positioned or possessing extraordinary acceleration capabilities. Yet, the scientific rewards would be immeasurable. Samples from another star system, insights into the chemistry of a distant corner of the galaxy, and answers to questions we are only beginning to formulate. 3I Atlas is already billions of kilometers distant from the inner solar system. While we missed the opportunity to intercept it this time, it has demonstrated the potential of such encounters, revealing what lies beyond and igniting a desire for further exploration. Part 6. Citizen scientists catching ghosts. Occasionally, the most significant discoveries emerge not from sophisticated algorithms or machine learning, but from human eyes and intuition applied to data in a uniquely insightful way. And often, the individual responsible is not a professional astronomer. Consider the phenomenon of odd radio circles, or ORCs. If you haven't encountered them, you're not alone. Their discovery in the year 2019 makes them a relatively recent astronomical find. These are vast circular structures, detectable only in radio wavelengths, invisible to optical or infrared observation. When a radio telescope is directed toward specific regions of the sky, these perfect rings of radio emission become apparent, sometimes spanning hundreds of thousands of light years, appearing like cosmic smoke rings adrift in space. Their origin remains unknown. While the prevailing theory involves galactic winds or shock waves emanating from supermassive black holes, the truth is, we are still in the process of unraveling this mystery. They are genuinely enigmatic, and their detection is challenging due to their faintness and their tendency to blend into the radio background. Automated detection algorithms often overlook them, as they are typically designed to identify point sources or compact objects, rather than large, diffuse rings. This is where Radio at Home enters the picture. This citizen science initiative enlists volunteers to visually examine radio continuum maps, searching for anomalies. Participants aren't seeking anything specific. They are looking for the unusual. And in March of the year 2025, a volunteer identified something extraordinary, an object cataloged as RAJ131346 plus 500320. While the designation itself might not be particularly catchy, its nature is far more compelling. A pair of intersecting radio rings, two circles superimposed in the sky, forming a figure 8 pattern. This represents the most distant and powerful ORC discovered to date, found not by an automated system or a professional survey, but by an individual dedicating their time to scrutinize data. The discovery was made using low-frequency continuum maps from the Low-Frequency Array, LOFAR, a radio telescope network distributed across Europe. LOFAR generates vast quantities of data, an amount too substantial for professional astronomers to review manually. Automated pipelines process the majority of this data, flagging potential objects based on parameters like brightness and shape. However, these pipelines incorporate filters and thresholds designed to detect the anticipated rather than the unexpected. This is where human pattern recognition proves invaluable. Our brains possess a remarkable capacity for identifying outliers, discerning structure within noise, and flagging something as interesting even when the reason isn't immediately articulate. The volunteer who discovered RAJ131346.9 did not need to comprehend the physics of ORCs. They simply needed to observe the image and recognize that it appeared unusual. And they were correct. But this instance is not isolated. Radio at Home has identified numerous anomalies. Another volunteer detected a colossal radio galaxy surrounded by a peculiar ring structure. Yet another found a ring situated at the terminus of a jet, a feature that theoretical models had not predicted. These are objects that would have been lost within the overwhelming volume of data had humans not been actively observing. This underscores a broader lesson that extends beyond radio astronomy. We are entering an era of unprecedented data generation. The Vera C. Rubin Observatory, upon its activation, will produce 15 terabytes of data each night, a figure that will be sustained for a decade. No human team can possibly examine all of this data, nor can any set of algorithms capture every anomaly. We require a dual approach: machines to manage the bulk processing, and humans to identify the rare edge cases that defy existing templates. Returning to 3I Atlas, could a citizen scientist have flagged its anomalies earlier? Might someone examining spectral data have noticed the nickel without iron signature before professional astronomers? Or could someone monitoring cometary activity have questioned its unusual activity so far from the sun? Perhaps. However, the fundamental point is that anomalies like 3I Atlas benefit immensely from having as many observers as possible scrutinizing the data. While professional astronomers possess specialized knowledge, training, and context, they also operate with pre-existing expectations, models they aim to validate, and limited time. Amateurs and citizen scientists bring fresh perspectives, unburdened by assumptions about what should be observed. They are free to perceive what is actually present. Numerous accounts exist of amateur astronomers discovering supernovae, identifying asteroids, and tracking variable stars. The Japanese amateur astronomer Yuji discovered multiple comets and a supernova. British amateur Andrew Gray co-discovered an unusual stellar outburst. These are not mere coincidences. They exemplify the outcomes when passionate individuals, equipped with telescopes or data access, dedicate themselves to careful observation of the universe. In the future, as telescopes inundate us with petabytes of data, citizen scientists may well become the initial responders to cosmic curiosities, flagging the next interstellar comet, the next peculiar radio structure, or the next inexplicable phenomenon. Subsequently, professional astronomers will conduct follow-up investigations to elucidate the underlying physics. This represents a collaborative effort, and like all successful partnerships, its strength surpasses that of its individual components. Part 7. Citizen Science versus Professional Gatekeeping. However, it would be disingenuous to portray this as a purely harmonious relationship. A palpable tension exists. The integration of citizen science necessitates managing false positives, instances where well-intentioned amateurs flag observations that later prove to be artifacts or noise, and addressing conspiracy theorists who perceive alien signals in every data glitch. Professional astronomers understandably express concern regarding these issues. Organizations like the Royal Astronomical Society have extensively debated this topic. On one hand, citizen science alleviates data backlog, enabling projects to process more information than would otherwise be feasible, while also fostering public engagement and enthusiasm for science. On the other hand, rigorous quality control is paramount. A discovery is not considered valid until it has been independently verified, cross-checked, and subjected to peer review, a process that demands time and expertise. False positives pose a genuine challenge. An individual flags an object as unusual, prompting astronomers to spend days or weeks investigating, only to conclude it was instrumental noise, a satellite trail, or a cosmic ray impact. This diverts time that could have been allocated to genuine discoveries. When false positives accumulate, astronomers may become skeptical of citizen reports, leading to a diminished signal-to-noise ratio and observer fatigue. Confirmation bias also plays a role. When individuals are focused on finding a specific phenomenon, they are inclined to perceive it even in its absence. This is a human tendency that affects professionals as well, but training and peer review serve as crucial checks. Amateurs may lack these safeguards and might interpret random data as a genuine pattern, leading to claims of alien megastructures around Tabby's star or coded messages within pulsar timing residuals. Calibration and error margins present another concern. Professional astronomers are adept at assessing measurement uncertainty and distinguishing statistically significant signals from noise. Amateurs may not possess this expertise and might report a detection that is merely a 1 sigma fluctuation, statistically insignificant. Furthermore, limited resources are a factor. If a citizen science project gains excessive popularity, with numerous individuals flagging a multitude of items, the professional astronomers tasked with follow-up may become overwhelmed. They cannot investigate every report and must prioritize, potentially leading to genuine discoveries being overlooked due to the sheer volume of submissions. However, these challenges are not insurmountable. They are obstacles to be overcome rather than deal breakers. Training protocols can be instrumental. By educating citizen scientists on data quality assessment, artifact recognition, and uncertainty estimation, the rate of false positives can be significantly reduced. Mentorship programs, where experienced amateurs guide newcomers, can help maintain high standards. A tiered validation system, requiring multiple independent volunteers to flag the same object before it is elevated for professional review, can effectively filter out spurious detections. The potential benefits are substantial. Crowdsourcing anomaly detection allows for more thorough exploration of vast data sets. Independent verification by numerous observers minimizes the risk of overlooking a genuine anomaly due to individual oversight. Diverse perspectives can lead to the identification of patterns that specialists might miss. Bringing this back to 3I Atlas, could a citizen astronomer have flagged its nickel anomaly earlier? The spectral data is publicly accessible, and anyone with appropriate software can download and analyze it. However, spectroscopy is a complex discipline requiring an understanding of line identification, wavelength calibration, and signal-to-noise assessment, making it unsuitable for casual analysis. Nevertheless, with adequate training, guidance, and a collaborative community, it is conceivable that an individual might have noticed the anomaly before it garnered widespread attention. The same applies to its water production rate. Comet light curves, which measure brightness over time, are often contributed by amateur astronomers. If these amateurs had been examining ultraviolet data from the Swift satellite and had been trained to recognize unusual activity patterns, they might have flagged 3I Atlas's superlinear brightening. They could have indicated that its behavior was atypical for a comet prior to professional surveys confirming it. Past citizen-led discoveries validate this approach. The detection of exoplanets via the transit method, observing minute dips in a star's brightness as a planet passes in front of it, has been significantly advanced by citizen scientists analyzing Kepler data. Projects such as Planet Hunters have confirmed the discovery of numerous exoplanets. Amateur asteroid hunters have identified near-Earth objects that eluded professional surveys. Amateur nova hunters frequently precede professionals in discovering stellar outbursts due to their nightly observations with smaller telescopes, whereas professional telescope time is scheduled months in advance. The conclusion is not to replace professional astronomers with amateurs, which would be an absurd proposition. Rather, the conclusion is that both are essential. Professionals provide the deep expertise, theoretical frameworks, and rigorous validation. Citizen scientists contribute breadth of coverage, fresh perspectives, and a sheer abundance of observational power. This is not a competition, but a partnership, and in the era of overwhelming data, it is a necessary one. Part 8. The Coincidence Effect. The month of October in the year 2025 presented an unusual celestial spectacle. Viewing conditions were exceptionally favorable for both Mercury and Ceres. Mercury, the innermost planet, achieved a prominent position in the evening sky, appearing bright and elevated above the horizon shortly after sunset. Ceres, the largest celestial body in the asteroid belt, reached opposition, placing it directly opposite the Sun in the sky, thus appearing at its brightest and closest to Earth. On social media platforms, individuals began to draw connections. Mercury was visible, Ceres was visible, and concurrently, the peculiar interstellar comet 3I Atlas exhibited signs of activity. Were these events related? Was some cosmic alignment occurring? Could the gravitational forces of the solar system be influencing or amplifying the comet's behavior? To be unequivocally clear, the answer is no. There is no discernible connection. Mercury's orbital path has no bearing on the outgassing of an interstellar comet. Ceres's position relative to Earth exerts no influence on chemical processes occurring billions of kilometers away. These are independent occurrences that, by sheer coincidence, were observable simultaneously. Human beings are inherently predisposed to identifying patterns. It is a survival trait ingrained in our nature. Our ancestors who recognized correlations between certain berries and illness, or between specific animal tracks and the presence of prey, were more likely to survive than those who did not perceive such patterns. Consequently, our brains are exquisitely sensitive to patterns, sometimes to the extent of perceiving them where they do not actually exist. This phenomenon can be described as cosmic scale pareidolia. Pareidolia is the tendency to perceive familiar shapes, such as faces, in random patterns, like clouds or static. It represents a misapplication of pattern detection. Such occurrences are common with celestial events. Ancient cultures interpreted planetary alignments as omens. The appearance of a comet during a battle was believed to signify divine displeasure. The congregation of planets in a particular sector of the sky was thought to portend the birth or demise of royalty. The year 1910 provides a striking historical parallel. This was the year of Halley's Comet's return, as it traversed the inner solar system on its 76-year orbital path. Widespread fear gripped the public. Astronomers had detected cyanogen, a toxic gas, in the comet's tail. Newspapers published sensational headlines proclaiming, "Comet's poisonous tail will pass over Earth." In response, individuals procured gas masks, some sealed their windows, and tragically, there were reports of suicides among those convinced the comet would bring about their demise. Naturally, no such catastrophic events occurred. The comet's tail is exceedingly diffuse, essentially a hard vacuum by terrestrial standards. The quantity of cyanogen that actually reached Earth was negligible and undetectable. The comet posed no threat. However, the coincidental timing of the comet's appearance with unrelated events, solar activity, political unrest, earthquakes, fueled the widespread panic. People connected dots that were not intrinsically linked. We are witnessing a similar phenomenon today with 3I Atlas. The comet itself is unusual, genuinely anomalous. Mercury and Ceres happen to be visible concurrently, leading to the construction of speculative narratives. Perhaps the comet's activity is being triggered by some form of solar system resonance. Maybe its trajectory is being subtly influenced by gravitational perturbations. Perhaps this is all part of a larger, as yet unknown, cosmic pattern. Astronomers have performed the calculations. The gravitational influence of Mercury on an object in the outer solar system is virtually non-existent. Mercury is a relatively small planet, only slightly larger than our moon, and it is situated at a considerable distance. Ceres is even smaller and exerts even less gravitational influence. The combined gravitational pull of all planets in the solar system would be insufficient to significantly alter 3I Atlas's behavior at the observed distances. The comet's activity is driven by internal processes, solar radiation, and its own chemical composition, not by the fortuitous alignment of Mercury in its orbit. However, factual accuracy often takes a back seat to compelling narratives. The human brain craves stories. We desire connections between events because isolated occurrences can feel random, chaotic, and devoid of meaning. If the comet's activity is linked to planetary positions, it implies order, predictability, and significance. Conversely, if they are unrelated, it suggests we inhabit a universe where strange things simply happen, a notion that can be psychologically unsettling. Confirmation bias exacerbates this effect. Once individuals begin seeking connections, they tend to find them universally. Mercury was also visible during a previous comet discovery. Ceres was near opposition when another unusual object was identified. The fact that Mercury is visible multiple times a year and Ceres reaches opposition annually is overlooked. Similarly, the constant stream of unusual astronomical discoveries is disregarded. The brain selectively filters out non-coincidences, retaining only those that support the prevailing narrative. Social media amplifies this phenomenon exponentially. In the past, if one proposed a theory about planetary alignments influencing comets, the idea might have been dismissed by friends as nonsensical, effectively ending the discussion. Today, posting such a theory online instantly connects individuals with like-minded people. Links, images, and charts depicting alignments are shared. New evidence is contributed, and the information is disseminated further. Consequently, a comprehensive alternative narrative emerges, directly competing with the scientific explanation. The fundamental lesson isn't that individuals are easily misled or credulous. Instead, it highlights how coincidences hold significant sway, and our cognitive frameworks are not finely tuned to disregard them. Given the sheer volume of celestial events unfolding constantly, a certain number will inevitably align purely by chance. These coincidences will feel profound, even when they lack genuine significance. This understanding is crucial because it influences how people interpret unusual occurrences, such as the peculiar behavior of Comet 3 Atlas. If one is predisposed to perceive cosmic conspiracies and believes celestial alignments carry meaning, then the comet's anomalous actions can be interpreted as evidence of something larger. It might not be a natural celestial body at all. Perhaps it is manufactured. It could be reacting to signals emanating from planets, or it may be an integral part of a grand cosmic apparatus beyond our current comprehension. This leads us to an even more astonishing segment of this narrative: the mechanics behind deception, speculative theories, and humanity's tendency to transform scientific enigmas into cultural legends. Part 9. October 2025. An update. Did it truly transpire? October 8, 2025. Blue Origin mission NS-36. 6 voyagers, spanning 11 minutes. A single undisclosed passenger whose identity remained confidential until the craft's descent concluded. The module ascended, breached the Kármán line, drifted in zero gravity, parachuted back to Earth, and landed softly in the Texan desert. A triumph. Another impeccable voyage for the organization's space tourism initiative. This marked their 15th manned expedition. A routine occurrence. Almost. That's the official account. ABC News documented it. Medium published an article. A few space correspondents shared updates on social media. The concealed traveler was unveiled post-landing. a private citizen who had requested anonymity during the journey itself, but consented to public identification afterward. Nothing out of the ordinary there. Privacy is a purchased commodity frequently. However, this is where the peculiarity arises. This is what persistently bothers anyone closely observing space exploration. The profound quiet, the unsettling, almost stifling absence of widespread reporting. No viral videos, no trending hashtags, no celebrity commentary, humorous reinterpretations, or detailed analyses on platforms like TikTok. A space voyage, a commercial expedition venturing to the edge of space, something that, mere years prior, would have dominated headlines for an extended period. It barely registered as a ripple. Contemplate this for a moment. 6 human beings departed our planet. They experienced weightlessness, observed the curvature of Earth against the vast blackness of space, and returned safely. That is extraordinary. It ought to be heralded as extraordinary. Yet, the internet remained indifferent. Social media moved on within mere hours. The narrative dissipated like mist. Why? Why so little tangible evidence? Blue Origin typically releases footage from within the cabin. Stunning visuals of passengers floating, laughing, gazing out of the windows. Where were those images? Why weren't they disseminated across every news outlet? Why didn't the revelation of the mystery passenger spark curiosity? Who were they? Why did they desire discretion? These are natural inquiries, the kind that typically ignite days of speculation and public interest. Instead, nothing. Absolute silence. It's as if the flight occurred in a void, not merely of space, but of public attention. And that void, that lack, begins to feel like a presence in itself. The silence amplifies more than any official statement could. Doubt begins to creep in. Uncomfortable questions start to surface. Did this flight truly unfold as depicted? Were there indeed 6 passengers, or was the manifest altered? Was the hidden passenger a genuine individual, or a fabricated element to explain the absence of pre-flight publicity? Did the capsule actually lift off on October 8th, or was footage from a prior mission repurposed with a new date? These are thoughts born of suspicion, the hallmark of conspiracy thinking, the kind of reasoning that perceives threats in every shadow and trusts nothing. Yet, on occasion, the lack of evidence carries substantial weight. When something that should generate considerable attention remains conspicuously quiet, an explanation is warranted. Let us draw a parallel with April 2025. Merely 6 months prior, Blue Origin initiated another New Shepard mission, and that one ignited public fascination, not due to a malfunction, but because of its occupants. Prominent figures like Katy Perry and Gayle King, part of the inaugural all-female crew, individuals with massive online followings, the kind of passengers intentionally selected to generate headlines, and they succeeded. However, not in the way Blue Origin anticipated. Within hours of the live broadcast concluding, social media was ablaze with speculative theories. People alleged the flight was fabricated. They meticulously dissected every frame of the footage, searching for discrepancies. The way hair behaved in zero gravity became a focal point of intense scrutiny. Did it float correctly? Did it move with unnatural stiffness? Was it genuine hair, a wig, or digitally generated? The capsule's hatch presented another area of contention. Someone asserted it operated differently compared to previous missions. They presented side-by-side comparisons, annotated with arrows and circled details they deemed anomalous. Wasn't the locking mechanism on the opposite side previously? Didn't the door swing outward before? Why does this appear distinct? Then, the more outlandish claims emerged. Accusations of green screen usage, assertions that the passengers were filmed in a studio with simulated windows displaying pre-recorded views of Earth, claims that hands appeared artificial, excessively smooth, and plastic-like. Complaints surfaced regarding the absence of visible heat damage marks on the capsule after re-entry. Every minute detail was interpreted as evidence of deception. Journalists systematically refuted these claims. Hair behaves unusually in microgravity because gravity's pull is absent, causing it to react to air currents, static electricity, and random movements. The hatch mechanism is identical across all flights. Camera angles and lighting can create the illusion of differences. Reflections in visors can distort perspectives. Scorch marks may not always be apparent, depending on the dust accumulation at the landing site and the camera's resolution. Nevertheless, these refutations did not quell the theories. If anything, they seemed to bolster them. Those predisposed to believe the flight was fake interpreted the debunking efforts as an attempt at concealment. They delved deeper, unearthed more evidence, and constructed elaborate scenarios detailing how the alleged hoax was executed. The conspiracy theory became self-perpetuating. We now have two missions, both utilizing the same rocket and a similar flight profile, separated by 6 months. One generated an intense storm of attention and skepticism. The other barely made a whisper. And one must inquire, which scenario appears more suspect? Part 10. Celestial Enigmas as Reflections. The cosmos continually presents us with unexpected phenomena, objects that defy classification, signals that lack discernible meaning, events that contradict our carefully formulated models, and without fail, on every occasion, we undertake two actions. Firstly, we diligently strive to comprehend the scientific basis. Secondly, we project our own interpretations onto the mystery. Consider Oumuamua, observed in 1917. The initial confirmed object of interstellar origin traversing our solar system, it tumbled, possessed a reddish hue, was elongated, and notably, it accelerated. While the acceleration was modest, it was measurable as it departed the solar system. This acceleration could not be explained by a purely gravitational trajectory alone. Something was propelling it. Scientists proposed outgassing, even in the absence of detected gas emissions, suggesting it might have released minute quantities of volatile substances, generating thrust akin to a weak comet. Alternatively, it could have been a hydrogen iceberg, frozen H2, which would sublimate without visual indication. Another hypothesis suggested it was a fragment from a shattered planet, its shape and rotation contributing to radiation pressure effects. However, a segment of individuals, including some scientists, proposed an entirely different explanation. What if Oumuamua was artificial, a light sail propelled by solar radiation pressure? This would account for the observed acceleration. And if artificial, it might have been a probe dispatched by an alien civilization engaged in exploration. Or perhaps it was a derelict artifact, remnants of a long-vanished extraterrestrial society. A similar situation arose with Tabby's star, KIC 8,462,852. A star within the Kepler field of view exhibited peculiar dimming patterns characterized by deep, irregular fluctuations in brightness, sometimes dropping by 20% or more. No celestial body of planetary size could account for such a significant blockage of light. Furthermore, these dips did not occur with the regularity expected of planetary transits. Astronomers posited the presence of dust clouds, vast swarms of comets, or debris from a planetary cataclysm. However, one academic paper, presented somewhat facetiously, suggested the existence of an alien megastructure, a Dyson swarm. This hypothesis envisioned millions of solar panels or habitats orbiting the star harvesting its energy and irregularly obscuring its light as these structures moved. This explanation, to some extent, aligned with the observed data. Odd radio signals, fast radio bursts, the Comet 3 Atlas. Every enigma becomes a canvas onto which we project our deepest hopes and most profound fears. Are we solitary beings? Does the universe operate with indifference or with intent? Are there other intelligences present? And if so, do they resemble us, or are they utterly beyond our comprehension? The underlying psychology here is potent. Pareidolia, the tendency to perceive familiar patterns in random stimuli, plays a significant role. We discern faces in clouds, detect voices in static, and attribute intelligence to celestial anomalies. This is not indicative of intellectual deficiency. Rather, it is a fundamental aspect of how our brains function. We are, in essence, sophisticated pattern recognition engines, and we possess an inherent bias towards identifying false positives. It is more advantageous to mistake a shadow for a predator than to overlook a genuine predator because it resembles a shadow. Furthermore, there exists a deep-seated existential yearning. We crave connection, the assurance that we are not merely isolated sparks of consciousness adrift in an immense, cold cosmos. Every anomaly represents an opportunity, a possibility, a gateway that might lead to something truly extraordinary. And so, we persistently explore these possibilities with great intensity. The Comet 3 Atlas serves as a mirror. Within its luminous green halo, we see reflected our own innate curiosity, our profound desire for meaning, and our fervent hope that the universe is far more wondrous and enigmatic than we currently imagine. And perhaps, indeed, it is. It is conceivable that one day we will encounter something genuinely inexplicable, something that compels us to revise the very foundations of physics or to accept the reality that we are not alone. However, that moment has yet to arrive. For the present, we are observing a comet, an unusual comet, a captivating comet, but likely still just a comet. And that, in itself, is significant, because even natural mysteries possess an inherent extraordinariness. Part 11, the Archive of Extraterrestrial Systems. Conceive of the galaxy as a vast repository of knowledge, not a collection of written works, but of physical entities, comets, asteroids, rogue planets, all ejected during the tumultuous formation of planetary systems and propelled into the interstellar void. Each of these objects can be likened to a message in a bottle, carrying encoded information about the stellar system from which it originated. And on occasion, one of these vessels washes ashore in our cosmic neighborhood. This is the essence of interstellar objects. They are like dispatches from distant star systems, not alien in the sense of intelligent extraterrestrial life, but alien in the sense of being foreign, dissimilar, having formed under conditions markedly different from those within our own solar system. Each one we detect provides a crucial data point, a singular sample. And with a sufficient quantity of these samples, we begin to grasp the spectrum of chemical compositions found in planetary systems. The comets within our solar system exhibit a remarkable degree of uniformity. They coalesced within the same protoplanetary disk, from a homogeneous mixture of gas and dust, subjected to an identical stellar radiation field. Certainly, variations exist. Some are richer in carbon monoxide, others in water, depending on their initial location within the disk and the temperatures they encountered. However, they are all fundamentally akin, belonging to the same celestial family, perhaps distant relatives at most. Interstellar comets, conversely, are strangers. They originated elsewhere, under different stars, within disks possessing distinct compositions, temperatures, and dynamical environments. And to date, every one we have observed has presented unique characteristics. Oumuamua, dry, lacking detectable outgassing, unusually shaped, and exhibiting mysterious acceleration. It bore no resemblance to our comets, nor did it behave like them. If it was a comet at all, it belonged to a category entirely new to our experience. Comet Borisov, rich in carbon monoxide. Its behavior was largely typical of a comet, but with a gas-to-dust ratio indicative of a formation environment colder than that of most of our comets. It appeared familiar, yet subtly anomalous, akin to a dialect of a language one already speaks. Comet 3 Atlas, exhibiting vigorous expulsion of water and carbon dioxide at considerable distances, an unusual absence of iron in relation to nickel, and the late appearance of cyanide. None of its observed behaviors align with our established understanding. It communicates in a language we can barely decipher. 3 distinct objects, each displaying wildly divergent chemical signatures. If we extrapolate from these findings, assuming these 3 are representative of the broader cosmic population, then the diversity of cometary compositions across the galaxy is truly staggering. Not all planetary systems yield comets comparable to ours. In fact, it is plausible that most do not. Consider the implications of this. In some systems, comets might be predominantly composed of nitrogen ice, akin to Pluto's surface. In others, methane could be the primary volatile. In systems orbiting more massive stars, the frost line, the region where water ice can condense, is situated further from the star. Consequently, comets may form in colder zones and contain different volatile mixtures. In systems with migrating gas giants, the disk experiences significant turbulence, mixing materials from various temperature zones, resulting in comets with peculiar hybrid compositions. Is it possible that some comets carry molecules we have never encountered? Molecules that are thermodynamically feasible, but necessitate formation pathways absent in our solar system. Exotic organic compounds, unusual ices, substances that would ignite a chemist's enthusiasm. It is highly probable, given the immense scale of the universe. The spectrum of stellar masses, disk compositions, radiation fields, and dynamical environments is vast. Nature actively explores this entire spectrum, and some of the resultant phenomena are bound to be extraordinary. Now, let us delve deeper. If life requires specific chemical precursors, such as water, organic compounds, phosphorus, nitrogen, and sulfur, then comets lacking these essential ingredients would be sterile. They would be incapable of seeding life or delivering prebiotic chemistry to planets. It is possible that many interstellar comets are indeed sterile. Perhaps Oumuamua was merely a lifeless rocky body traversing the void. However, if even a small fraction of comets harbor the correct chemistry, that fraction holds immense importance. This is because comets are cosmic wanderers, traveling between stars, traversing vast distances measured in light years. And if they carry organic molecules, amino acids, perhaps even dormant microorganisms shielded within their interiors, then the fundamental building blocks of life can indeed propagate across the galaxy. This concept is known as panspermia, the hypothesis that life can be transferred between celestial bodies via comets or asteroids. It remains a controversial and unproven theory, but it is not impossible. And Comet 3 Atlas, with its water, its organic compounds, and its cyanide, certainly possesses the necessary ingredients. Not life itself, most likely, but the chemical precursors that could lead to life if delivered to a suitable planet. Every interstellar object we detect expands our sample size. Currently, we have 3, In a decade, we might have dozens. In 50 years, possibly hundreds. And with each new discovery, we will meticulously measure its composition, trajectory, and activity patterns. We will develop a statistical understanding of what exists beyond our solar system. It is possible we will find that water-rich comets are commonplace and that most planetary systems produce them. Or perhaps we will discover that our solar system is the anomaly, that water-rich comets are rare, and that most systems generate dry, carbonaceous bodies. Either conclusion holds profound fascination. And perhaps, just perhaps, we will encounter a comet exhibiting clear biomarkers, molecules that are difficult to explain without biological origins, such as phospholipids, complex organic structures with chirality, or isotopic ratios that strongly suggest metabolic processes. Such a discovery would be revolutionary, confirming that life arose independently elsewhere and that biochemistry is not a phenomenon unique to Earth. We have not yet made such a definitive finding. As far as we can ascertain, Comet 3 Atlas is not carrying life. However, it is transmitting invaluable information. And information is the fundamental currency of scientific advancement. Every interstellar visitor is a gift, a gratuitous sample delivered directly to our doorstep. All that is required of us is to observe with sufficient diligence. Part 12. Nickel serves as a messenger. Let us revisit the anomaly concerning nickel, as it transcends mere curiosity. It represents a crucial clue, a unique chemical signature, and these signatures provide insights into an object's origin. Stars function as cosmic forges. Through nuclear fusion in their cores, they transform hydrogen and helium into heavier elements: carbon, nitrogen, oxygen, silicon, sulfur, and iron. Subsequently, when massive stars culminate their existence in supernova explosions, these cataclysmic events give rise to even heavier elements, including nickel. These elements are then dispersed into space, intermingling with gas clouds, and eventually becoming incorporated into the formation of new stars and planets. However, not all stars are born with the same elemental composition. The abundance of heavy elements, a characteristic astronomers refer to as metallicity, varies significantly. Young stars, formed recently from gas enriched by numerous supernova events across generations, exhibit high metallicity. Conversely, older stars, which coalesced when the galaxy was younger and fewer supernova explosions had occurred, possess lower metallicity. Both nickel and iron are products of supernova events, but their relative proportions can differ depending on the specific type of explosion. Type Ia supernovae, occurring when a white dwarf star accretes matter and detonates, produce different nickel-to-iron ratios compared to core collapse supernovae, which result from the implosion of massive stars. If Comet 3 Atlas originated in a system whose primordial gas cloud was enriched by an unusual combination of supernova types, its nickel-to-iron ratio might be skewed. Current scientific understanding suggests that Comet 3 Atlas may originate from the thick disk population, an older group of stars. Stars in the thick disk generally have lower overall metallicity, but the ratios of different heavy elements can fluctuate. If the observed decoupling of nickel, as seen in Comet 3 Atlas, reflects the composition of its parent star system, then this comet acts as a tracer. It provides information about galactic chemical evolution in ways that are otherwise difficult to access. The reason for this is that while we can analyze stellar atmospheres spectroscopically, measuring their iron, nickel, and other elements, stars are incredibly distant. We can only study a minute fraction of them in detail. Furthermore, we are unable to study stars that no longer exist, stars that lived and died billions of years ago. However, comets originating from those systems serve as time capsules, preserving the chemical conditions of their birthplaces. If we were able to directly sample Comet 3 Atlas, analyzing its isotopes, trace elements, and mineral structures, we would be holding a fragment of a star system that could be billions of years old and thousands of light years away. We would be deciphering a history written in the language of atoms. Now, let us entertain a speculative, albeit fringe, idea that circulates in certain scientific communities. Could elemental anomalies like an elevated nickel content be indicative of processed material, not processed naturally, such as through thermal metamorphism, but processed through technological means? If an advanced civilization were engaged in mining asteroids, refining metals, and constructing structures in space, they would inevitably generate waste products, slag, tailings, and exhaust. Such material would likely exhibit unusual elemental ratios because industrial processes are inherently selective. For instance, iron might be extracted for construction, with nickel-rich residue being discarded, or nickel might be utilized for a specific application, with all other elements being disposed of. If a comet formed within a debris disk containing such industrial waste, it could incorporate these anomalous metals. Subsequently, over millions or billions of years, this comet could be ejected, wander through the galaxy, and eventually arrive in our solar system. We would then detect the nickel anomaly and be left to ponder its origin. To be unequivocally clear, there is currently no evidence to suggest that Comet 3 Atlas is artificial or contaminated by technosignatures. 0. The concept is so speculative as to verge on science fiction. The vast majority of scientists dismiss it outright. However, it is not physically impossible. And in the absence of a definitive natural explanation for the nickel-iron decoupling, even highly unconventional ideas receive consideration. The more probable explanation lies in prosaic chemistry. Nickel incorporated within organometallic compounds, fractionation occurring during condensation, or some as yet undiscovered process that operates under conditions prevalent in other star systems but are rare or absent in ours. However, what truly ignites my scientific curiosity is this. Every comet carries a chemical signature, a unique barcode encoded in its constituent elements and isotopes. If we can compile a comprehensive catalog of these signatures, meticulously documenting the compositions of dozens or even hundreds of interstellar objects, we can begin to map the intricate structure of the galaxy. We could correlate these chemical signatures with their trajectories. A comet originating from the direction of the galactic center might exhibit different elemental abundances compared to one originating from the outer halo. A comet from the thick disk could reveal age-related signatures. We could effectively utilize comets as indicators of galactic structure and its evolutionary history. Imagine a future scenario where interstellar objects are detected with such frequency, and our technological capabilities for detection are so advanced that we are cataloging them by the dozens each year. Each object would undergo spectroscopic analysis, and its trajectory would be traced back as far as our instruments allow. Each individual's findings contribute to a collective repository of information. Over time, discernible patterns begin to emerge. We observe that comets originating from a particular galactic sector exhibit a consistent enrichment of carbon. Conversely, comets from another region are demonstrably richer in water. This allows us to begin deciphering the underlying reasons. It's plausible that the carbon-rich zones were the birthplace of more low-mass stars, which in turn possess planetary disks with distinct chemical compositions. Alternatively, the water-rich areas might have experienced more supernova activity, thereby seeding the surrounding gas with oxygen. 3 Atlas represents the inaugural entry in this burgeoning scientific archive. While it is a solitary contribution, a single data point, it signifies a crucial beginning. And the peculiar, seemingly disconnected presence of nickel serves as a potent reminder that every piece of information carries an intrinsic narrative. Each ratio of elements discovered represents a vital clue. With diligence and careful observation, we can unravel these narratives and reconstruct the grand chronicle of the galaxy itself. Part 13 delves into the unseen population, 3 celestial bodies, specifically 2 interstellar visitors, designated I Borisov and 3 I Atlas, have been definitively identified within a 7-year span. While this number may seem modest, it is sufficient for statistical analysis, enabling us to estimate the abundance of other interstellar objects traversing our solar system undetected. Astronomers have meticulously analyzed detection frequencies, survey coverage areas, and the observed characteristics of these 3 entities. Their calculations suggest that at any given instant, there are likely several interstellar objects residing within Jupiter's orbital path. These objects are small, dark, and move with considerable speed, rendering them invisible to the majority of our observational instruments. Our success in detecting these 3 is attributed to sheer luck. They happen to pass in close proximity to Earth, possess sufficient brightness, or were observable by the appropriate telescope at the opportune moment. How many have we overlooked? Potentially hundreds, or even thousands. For every interstellar comet we successfully identify, it is probable that dozens more pass through unnoticed. Some are simply too faint to be detected. Others traverse at speeds too great for us to track effectively. Still others emerge within regions of the sky that are not currently under surveillance. Detection is inherently challenging, yet the capabilities are continually improving. New observational surveys are coming online, offering unprecedented sensitivity and expansive sky coverage. The Vera C. Rubin Observatory, currently under construction in Chile, is designed to meticulously scan the entirety of the visible sky every few nights, capturing images of celestial objects down to remarkably faint magnitudes. This instrument will be instrumental in identifying asteroids, comets, supernovae, and indeed, any object exhibiting motion or variability, including interstellar visitors. Projections indicate that the Rubin Observatory could potentially detect 1 interstellar object per month and possibly more. This translates to a minimum of 12 such objects annually. Over a decade, this could lead to the confirmed identification of over 100 interstellar visitors, providing a statistically significant sample. This volume of data will be sufficient to commence drawing robust conclusions regarding their compositions, origins, and population distributions. Furthermore, the Square Kilometre Array, a network of radio telescopes currently under construction in Australia and South Africa, is expected to make significant contributions. Radio wave observations possess the capability to detect molecular emissions emanating from comets, even those of low luminosity. The SKA has the potential to identify interstellar comets that might elude optical telescopes. Space-based telescopes operating in the ultraviolet and infrared spectrums will be crucial in observing comets that are actively outgassing but remain obscured at visible light wavelengths. Each new instrumental advancement expands our detection capacity, enhancing our ability to perceive these faint, swift wanderers. However, detection represents only one aspect of the scientific endeavor. The study of these objects is another. At speeds often exceeding 50 kilometers per second relative to the Sun, by the time we detect them, analyze their orbital paths, and schedule follow-up observations, they are frequently already on their outward trajectory. Oumuamua was already departing our inner solar system when it was discovered. We managed one brief period of observation before it faded into the distance, too faint for further study. We intercepted Comet Y Borisov during its inbound journey, affording us several months for extensive observation. Telescopes worldwide were trained upon it, yielding valuable spectral data, light curves, and detailed observations, the ideal scenario. Comet 3. I-Atlas was also detected relatively early in its approach. We are currently acquiring valuable data, but it will soon reach its closest point to the Sun, swing around, and recede back into the cosmic darkness, becoming permanently lost to us unless we manage to intercept it. Proposals are in development for missions specifically designed to intercept interstellar objects. These missions would involve spacecraft launched rapidly, capable of achieving high velocities to rendezvous with an interstellar visitor while it remains within the inner solar system. The technical hurdles associated with such missions are substantial. A spacecraft would need to be maintained in a state of readiness for immediate launch. Advanced propulsion systems would be required to match the object's considerable velocity. Furthermore, sophisticated instrumentation would be necessary for compositional analysis, structural examination, and potentially sample collection. Nevertheless, the potential scientific rewards would be extraordinary. Imagine landing on an interstellar comet, excavating its surface, and collecting ice and rock fragments from another star system to be transported back to Earth for detailed laboratory analysis. The scientific insights obtainable from such material are almost beyond comprehension. We could determine precise isotopic ratios, offering invaluable information about nuclear processes within the parent star. Complex organic molecules could be analyzed with a level of detail unattainable through remote observation. The search for amino acids and prebiotic chemistry could be undertaken, and with extraordinary fortune, we might even discover fossilized microbial life. Even in the absence of biological findings, we would gain an exquisite understanding of the chemical intricacies of alien planetary systems. Every molecule, every mineral, every isotope would serve as a crucial piece of evidence. Certain scientists are already engaged in the planning stages for such missions. Conceptual designs exist, and funding proposals are being formulated. This is not a flight of fancy. It is a formidable engineering challenge, but one that is achievable. Within 50 to 100 years, we might have cataloged hundreds of interstellar objects, intercepted a dozen, and successfully returned samples from half a dozen. This accumulated data would provide a comprehensive understanding of galactic comet populations, the diversity of planetary systems, and potentially the prevalence of life's fundamental building blocks throughout the galaxy. Comet 3 I-Atlas offers a preliminary glimpse into this realm of possibilities. It demonstrates that interstellar comets are not merely rare curiosities, but are in fact commonplace, ubiquitous, and carry information of immense scientific value. The largely undetected population is out there, drifting through the void, awaiting discovery, and we will find them. Gradually, individually, we will catalog them, study them, and assemble the intricate puzzle of planetary system formation, variations in galactic chemistry, and perhaps the true prevalence of life. Part 14, entitled When Anomalies Accumulate, begins at time 0.5 seconds. Let us broaden our perspective and examine the larger context, as Comet 3 I-Atlas is not the sole perplexing phenomenon currently engaging the attention of astronomers. Far from it. We have peculiar radio circles, enigmatic rings of radio emissions whose origins remain unknown. Fast radio bursts, brief millisecond duration pulses of radio energy originating from distant galaxies, with their underlying mechanisms still under debate. Tabby's star, exhibiting bizarre dimming patterns that have not been fully elucidated. Oumuamua, an interstellar object noted for its anomalous acceleration. And Comet 3 I Atlas itself, a comet displaying an inexplicable rate of water production and unusual metallic signatures. These are merely the most high-profile examples. Dozens, perhaps hundreds, of lesser-known anomalies exist. Transient events that defy classification, spectral features that should not be present, and objects moving in ways that resist straightforward explanation. Astronomy is currently encountering a deluge of phenomena that do not conform to established understanding. This is a relatively recent development. Throughout most of the 20th century, astronomical data was scarce. Astronomers would direct a telescope towards an object, capture an image or a spectrum, and dedicate months to its analysis. Discoveries were infrequent, and anomalies even rarer. When an unusual observation did arise, it received intense scrutiny due to the limited competition for attention. Today, we are inundated with data. Automated surveys generate terabytes of information nightly. Sky surveys meticulously catalog billions of celestial objects. Gravitational wave detectors record cosmic mergers. Radio telescopes continuously scan the sky. We are detecting far more objects than we can possibly investigate thoroughly. With such a high volume of data comes an elevated rate of anomalies. If one examines 1 billion objects, even if only 1 in 1,000,000 exhibits unusual characteristics, that still amounts to 1,000 anomalies. The majority will likely prove to be instrumental errors, data glitches, or misclassifications. However, a subset will be genuine discoveries, and their thorough investigation requires considerable time. We are currently in an era where anomalies are outpacing theoretical explanations. We are discovering phenomena at a faster rate than we can comprehend them. This situation is both exhilarating and fraught with peril. It is exciting because novel phenomena serve as catalysts for new physics. The discoveries of pulsars, gamma-ray bursts, and gravitational waves all originated from unexplained observations. Anomalies are indeed the fertile ground for breakthroughs. However, it is also dangerous because the tendency for hype cycles to escalate out of control is significant. Every anomaly is frequently sensationalized as potentially revolutionary, evoking hypotheses of alien megastructures, warp drive signatures, wormholes, or exotic dark matter interactions. The media thrives on such narratives, and the public is captivated. Consequently, in roughly 9 out of 10 instances, the anomaly is eventually explained by a mundane phenomenon: dust clouds, instrumental noise, or the misidentification of known objects. The primary danger lies in the erosion of credibility. When individuals repeatedly encounter claims of potential alien involvement that are subsequently debunked as mere dust, they may cease to trust scientific pronouncements, perceiving science as mere wild speculation. Worse still, some may double down on the extraordinary explanation, concluding that scientists are actively concealing information. Tabby's star serves as a cautionary tale. When the hypothesis of an alien megastructure gained widespread media attention, the public enthusiastically embraced it. Social media buzzed, and news outlets eagerly reported on it. When subsequent observations revealed wavelength-dependent dimming, indicative of dust rather than solid structures, considerable backlash ensued. While some accepted the scientific explanation, others insisted that the scientists were mistaken or deliberately misleading. However, the situation with Tabby's star remains scientifically compelling. The dust explanation does not fully account for all observed data. Long-term monitoring reveals complex variability patterns. It is undeniably a peculiar star, possibly encircled by a debris disk resulting from a planetary collision or exhibiting some phenomenon that we do not yet fully comprehend. It remains a subject of valuable scientific inquiry, albeit not one involving extraterrestrial artifacts. The key lesson is that anomalies present opportunities. They compel us to refine our existing models, consider novel mechanisms, and challenge our fundamental assumptions. Even when they do not lead to revolutionary shifts in physics, they invariably advance our understanding. Oumuamua anomalous acceleration, even if attributable to outgassing, prompted scientists to engage in more profound contemplation of sublimation processes at low temperatures, exotic ice compositions, and surface properties. This represents genuine progress. Comet 3. I-Atlas offers another such opportunity. Its prolific water production challenges our current understanding of volatile sublimation distances. Its peculiar nickel anomaly compels us to reconsider metal chemistry in comets, a subject largely overlooked due to the absence of strong metallic emissions in our own solar system's comets. Its pronounced dominance of carbon dioxide raises questions about the conditions present in protostellar disks of other systems. When a sufficient number of anomalies are observed in conjunction, discernible patterns may begin to emerge. It is conceivable that odd radio circles and fast radio bursts are interconnected, perhaps both being manifestations of energetic outflows originating from galactic centers. It is possible that interstellar objects like Oumuamua and 3I Atlas represent distinct populations with differing formation mechanisms. The transient zoo of astronomical phenomena currently being observed might be conveying fundamental insights into the energetic nature of the universe. Alternatively, these anomalies may be entirely unrelated, individual quirks that happen to coincide within this relatively short observational period due to our newfound technological capabilities. Either conclusion provides valuable information. The critical approach involves simultaneously maintaining a healthy skepticism and a sense of wonder. One can be enthusiastic about an anomaly without prematurely declaring it a paradigm-shifting discovery. It is possible to investigate intriguing possibilities without becoming rigidly attached to them. Furthermore, one must be open to revising one's conclusions when new evidence emerges. This underscores the importance of effective science communication. When reporting on Comet 3I Atlas, responsible journalists and scientists should articulate the situation with precision, stating something akin to, "This comet is exhibiting unusual behavior. We are investigating several potential explanations, and here is what we have confirmed thus far." Rather than resorting to sensational headlines like "Alien Comet Defies Laws of Physics" or "Scientists Baffled by Impossible Object," the emphasis should be on nuance. However, nuance often fails to generate significant readership or viral attention. Precise language rarely achieves widespread dissemination. Consequently, the machinery of hype continues to operate, transforming every anomaly into a potential revolution and subsequently setting the stage for disappointment when a mundane explanation is eventually revealed. The solution is not to cease reporting on anomalies. Instead, it lies in being transparent about the uncertainties involved, presenting a spectrum of plausible hypotheses, and diligently updating information as new evidence becomes available. The public should be treated as intelligent individuals capable of comprehending ambiguity, as most people are. The majority of individuals understand that science is an iterative process, that answers evolve over time, and that acknowledging a lack of current knowledge is a perfectly acceptable response. Comet 3. I-Atlas represents one anomaly within a larger pattern. It is significant and fascinating, but it does not yet constitute definitive proof of anything extraordinary. It is a data point, a mystery, and an invaluable opportunity for learning. Regardless of whether its ultimate explanation involves a peculiar natural comet or an entirely unprecedented phenomenon, the process of studying it, rigorously testing hypotheses, and systematically eliminating explanations is inherently valuable. This process is the essence of science, and science, when conducted with integrity, stands as one of humanity's most profound achievements, particularly when grappling with subjects that currently elude our complete understanding. Part 15, titled Final Reflections, Alive Yet Natural, commences. We have now spent thousands of words delving into the enigma of Comet 3 I Atlas, an interstellar visitor spewing water into space from a location where such activity is not expected. It glows with a verdant hue due to nickel and cyanide, its emissions waxing and waning as if controlled by a deliberate hand. It carries the chemical signatures of another star system, possibly from an earlier epoch of our galaxy's history. Is it alive? In a metaphorical sense, perhaps. It exhibits dynamism, change, and responsiveness to its environment. It is active when it should be dormant, behaving in ways that appear purposeful, even though we understand these behaviors are governed by the laws of physics and chemistry, not by conscious intent. But alive in a literal biological sense? Almost certainly not. There is no empirical evidence suggesting biological processes, no metabolic functions, no capacity for reproduction, no mechanisms for information storage and transfer, none of the defining characteristics of life as we currently understand it. Comet 3 I Atlas is, in essence, a celestial body composed of rock and ice, warmed by solar radiation, releasing gas and dust in accordance with physical principles. Yet, these physical principles are manifesting in ways we have not previously observed. Water sublimation at extraordinary distances from its presumed stellar source. Nickel emissions devoid of associated iron, a pronounced dominance of carbon dioxide. Its intermittent emission behavior suggests a complex internal structure or the presence of exotic ice compositions. Each observation adds another layer to this intricate puzzle. So, what is it? The most probable explanation is that Comet 3 I Atlas is a naturally occurring comet formed under conditions vastly different from those prevailing in our own solar system. It might have originated farther from its parent star, in a colder region where carbon dioxide ice is more abundant than water ice. Its parent star might have possessed an unusual elemental composition, leading to its peculiar metallic ratios. Alternatively, prolonged exposure to space weathering over billions of years of interstellar travel could have altered its surface chemistry. The organometallic hypothesis is particularly intriguing. If nickel became integrated into volatile compounds, such as nickel carbide, this could account for its decoupled emissions. This scenario would necessitate specific chemical conditions during its formation, but it is not an insurmountable impossibility, merely unusual. The theory of its origin in a protoplanetary thick disk is also compelling. If Comet 3 I Atlas is approximately 7 billion years old, and if it carries isotopic signatures indicative of an earlier phase of galactic chemistry, this could explain some of its observed peculiarities. Ancient ices, ancient chemical compositions, and ancient minerals, all preserved in the frigid environment of interstellar space, are now being revealed as the comet approaches a star and heats up. Could it be artificial? Could it be a probe, a derelict spacecraft, some form of technological artifact? The available evidence does not support such a conclusion. Nothing about Comet 3 I Atlas necessitates a technological explanation. All observed phenomena can be, or at least potentially can be, explained by natural processes. Invoking extraterrestrial intelligence is therefore unnecessary. However, let us briefly entertain this speculative possibility. If one were tasked with designing an object to survive an interstellar journey and remain detectable billions of years later, how might they proceed? A likely approach would be to utilize a comet-like object as a protective shell, shielding the internal payload with ice and rock. Unusual chemical signatures might be incorporated as deliberate markers, designed to stand out to anyone analyzing the object's spectrum. Natural sublimation, as the object approached a star, would then gradually reveal these markers. This line of reasoning is purely speculative, lacking any supporting evidence. However, it is worth noting that if we were to encounter an artificial interstellar object, it might not initially appear artificial. It could resemble a comet, perhaps a peculiar one, but one that could be plausibly explained as natural until subjected to more rigorous examination. Is Comet 3I Atlas such an object? Probably not, almost certainly not. However, the very fact that we are posing the question is significant. It indicates that this comet is sufficiently strange to stimulate our imagination, prompting us to contemplate possibilities that we would typically dismiss. Perhaps this is its most profound value, not whether Comet 3I Atlas is natural or artificial, or whether its chemistry is merely unusual or genuinely revolutionary, but that it compels us to think. It challenges our preconceptions and reminds us that the universe is far vaster and more complex than our immediate surroundings suggest. Nature has had billions of years and countless star systems to explore the vast expanse of chemical possibilities, and we have only just begun to survey the scope of what is achievable. Every interstellar visitor presents a challenge. It tests our models, our theories, and our established notions of normalcy. And it is through confronting these challenges that we achieve growth. Oumuamua challenged our understanding of cometary activity. Comet I Borisov questioned our assumptions regarding the abundance of carbon monoxide. Comet 3I Atlas, however, challenges fundamental aspects of our understanding: volatile budgets, the chemistry of metals, the distances at which activity occurs, and the diversity of compositional types. The subsequent steps are clear. We must continue to observe Comet 3I Atlas as it approaches its perihelion. All available instruments should be utilized to measure everything possible: spectral data, light curves, gas production rates, and the ratios of dust to gas. We should search for new emission lines and observe whether iron eventually appears or if the nickel anomaly persists. These observations must be compared against theoretical models, leading to refinements in those models and the generation of new predictions. These predictions then need to be tested. Simultaneously, we must prepare for the arrival of the next interstellar visitor, as there will undoubtedly be more. The galaxy is teeming with these wanderers, and our detection technology continues to improve year by year. Each new arrival will present a fresh puzzle, a new set of clues, and a unique window into the processes of planetary system formation and evolution across a diverse range of stellar environments. Perhaps one day, we will achieve an interception. We will land on such an object, drill into its interior, and return samples to Earth. We will analyze its isotopic composition in terrestrial laboratories, study its minerals using electron microscopes, and meticulously search its organic inventory for prebiotic molecules, thereby uncovering knowledge that we cannot even conceive of at present. Until that day arrives, we will continue to observe, measure, and ponder, for this is an intrinsic aspect of human nature. We gaze at the universe and pose questions. Why is that comet exhibiting activity so far from its star? Where did it originate? What can it teach us? The questions themselves hold inherent value, even in the absence of immediate answers, because questions are the very foundation upon which exploration is built. Comet 3. I-Atlas journeyed from an unknown point across light years and billions of years, carrying a message encoded in water, nickel, and cyanide. We did not solicit this message, nor do we yet fully comprehend its content. However, we are listening, we are observing, and we are learning. And in this very act of learning, in this persistent determination to understand, we discover something that might be the closest approximation to life within this entire narrative. Not the comet itself, but us, curious, wondering, reaching out to touch something that originated from an impossibly distant realm, striving to decipher a communication from another world. The universe persistently dispatches these missives, cosmic postcards, messages in bottles, visitors from the darkness, and with each arrival, we are reminded that we inhabit a vast, ancient, and incomprehensibly rich cosmos, a cosmos that will perpetually surpass our comprehension, perpetually surprise us, and perpetually offer new mysteries. Comet 3. I-Atlas is one such mystery, a single comet within an infinite sky. Yet, it is now our mystery, and whether its nature is simply that of ancient ice or something more profound, whether its secrets yield readily or resist revelation for decades, we will persist in our search. We will continue to ask questions. We will remain attentive, listening for what the universe endeavors to communicate. For this is what it signifies to be human, to perceive something unusual in the night sky, and to refuse to avert one's gaze, to demand answers even when the universe remains silent, to find wonder in a plume of water molecules expelling at 40 kilograms per second, in the emerald glow of nickel where it ought not to be, in a trajectory pointing back towards stars we will never reach. We are small. The universe is immeasurably vast. Yet, separating us from that immense expanse, between the lenses of our instruments and those far-flung celestial travelers, between our persistent inquiries and any revelations that might emerge, a dialogue unfolds. This is a deliberate exchange, stretching across eras and the vast gulfs of space, articulated through the language of light particles, the signatures in starlight, and the elegant ballet of celestial motion. 3-Atlas conveyed a message. We registered its transmission and remained attentive, anticipating its further pronouncements.